Good morning. After a relaxing afternoon, we are ready to begin the second half of the conference, and it is with Luca Reggio. He will talk about resource-sensitive model theory, a categorical view. Thank you.
Thank you very much, Pino. Can you hear me? Yes. Good morning, everyone. So I'd like to start by first thanking the organizing committee for the great job they're doing, and also the scientific committee for inviting me to give this talk. It's a real pleasure. I'm grateful and humble. What I'd like to do is to give an overview of the research program, which was started around 2017. Its aim is to provide a structural, categorical approach to what you may call a resource-sensitive model theory, trying to keep the technicalities to a minimum and rather convey the main ideas. And also explain to you what I mean by resources here. These are typically logical, syntactic resources. So I'll start by describing sort of a big picture and the kind of results and problems that you may encounter in this theory of logical resources, and in particular in finite model theory. And then in the second part, I will describe a categorical framework in which you can handle these logical resources. And in the third and last part, I'll show to you how you can use this framework to revisit some known results and establish new ones as well. Let me start by saying just a few words about categorical logic after being reviewed. This is by no means meant to be a complete introduction to categorical logic. I'm just picking a few key concepts here. So we know, thanks to Levier, that we can extend the very useful algebraic approach to propositional logic to industrial logic. And for instance, Lindemann-Tarski algebras are replaced by syntactic categories. And we also know that we can view quantifiers as adjoints to certain maps, and similarly for quality. So these are not extra structure, they are rather properties. And factorial semantics is telling us that we can and should view models as structure preserving functors defined on the syntactic category of theory. Let us say, a very useful tool in categorical logic is that of a hyperdoctrine associated with, say, first order theory T. And you can think of this as a fiber-wise Lindemann-Tarski algebras. It's a collection of Lindemann-Tarski algebras organized into functor. And the stratification here is in terms of three variables. In the formulas, whose equivalence classes are the elements of these Lindemann-Tarski algebras. So this means, in a sense, that you can study first order logic by studying Boolean algebras, therefore proposition logic, in a shift orders, in this case, or finite sense. There is a perspective which is dual to that of hyperdoctrines. And it was called, this notion was called a periodic space by André Joyal in a short announcement in the notices of the AMS in 1971. These periodic spaces, they encode the spaces of any types of first order theory. Here when I speak about type, I mean more than theoretical types. And this dual perspective was recently investigated and extended in several directions by Jeremy Marquez in his PhD thesis. So if you're interested in this point of view, talk to him, which should be here. All in all, this gives us a syntax-independent view of logic and model theory. So the next natural step is that of doing categorical model theory. There are various approaches. Again, here I will just mention a couple of them. The first one is based on accessible categories. And more recently, people have been looking into new abstract elementary classes. So this is a non-concrete version of Shelar's abstract elementary classes. And in both examples, the notion of compactness here, I mean the compactness theorem from first-order logic, is replaced by some rank accessibility category. And these tools are very useful if you're interested in studying infinite tree extensions of possible logic and monometry classes of mathematical structures. The perspective that I want to adopt for this talk is a bit different, and it's motivated by the needs of finite model theory and descriptive complexity, where people are usually interested in capturing structure which is down below. Typically, this means in fragments of the logic. So in a way, what we want is to have also categorical model theory, but which is well adapted to the needs of finite model theory and descriptive complexity, which means in particular that you should be able to handle these logical sources. And this suggests an orthogonal direction, which is that of dropping compactness altogether instead of replacing it by some degree of accessibility. But I think it's fair to say, to some extent, that finite model theory is model theory without compactness. This is because the compactness theorem, as well as the completeness theorem, they fail when restricted to finite structures. So if you're interested in finite models only, you should avoid using compactness. Okay, this doesn't sound very exciting, but there are some positive aspects if you can prove something without using compactness. Such a proof is usually more likely to admit a relativization to finite structures, and that's the main motivation. But it also typically carries some quantitative information about the objects and the constructing a proof. And this typically results in some stronger conclusions that hold not just for finite models, but typically also for infinite models. And I'll give you a few examples of this here in a minute. So if people do not use the compactness theorem, what do they use in the daily mathematical life? Well, they usually use combinatorics or game-theoretic arguments. So the challenge here is to bring back, if you wish, the tools of category theory and structural methods into this world of finite model theory and algorithmic model theory. So I'm going to present three examples, or rather families of examples, of theorems and problems in finite model theory, or more generally this resource-sensitive model theory, just to give you an idea of the kind of things people look at. So the first family concerns homomorphism preservation theorems. These are results that relate the syntactic shape of sentences with the semantic property of the formula sentence of being preserved under certain transformations between models. And the perhaps prototypical result is due to Walsh, Lindon, and Dusky in the 1950s, and they showed that if a sentence is preserved under homomorphisms between structures, if and only if it's equivalent to an existential positive one, which means one that does not use negation nor the universal quantifier. The proof of this result, the usual proof, uses the compactness theorem. However, then Rossmann came along, 2005, and showed that you can actually establish a quantitative improvement of the classical HPT, whereby you preserve the quantifier rank of sentences. The quantifier rank is the maximum nesting of quantifiers in formula, and this is the first example of logical resources that I was talking about. And this proof of this result, which is called the equirank HPT, does not use the compactness theorem. And with a bit more work, but quite a bit more work, but essentially using the same idea, you can improve the finite homomorphism preservation theorem. Again, going to that from the same paper, which is one of the fundamental theorems of finite model theory, and which basically says that the classical result by Walsh, Lindon, and Dusky admits a relativization to finite structures. So here you see how you obtain quantitative improvements of classical results and also useful relativizations. The second family of examples
just one. Existential positive means?
Yeah, so existential positive means that in your formula you do not use negation nor the universal quantifier. because you're only allowed to use conjunctions, disjunctions, and existential qualification. So model logic, I guess most of you would be familiar with it, so I'll be very brief. This is a logic where you have propositional atoms denoted by P, and then you have the usual Boolean connectives, conjunctions, disjunctions, and negation, and then you have two modalities, box and diamond. And model logic is interpreted of the structures that are usually called triplet models. The triplet model is just a set. Then you have, let's just say, one single binary relation that is called the accessibility relation of the model. And then you have a bunch of unary relations that tell you where the propositional atoms fall. And the validity of formulas in triplet models depends on the choice of the point. So you consider pointed models, and you say that the formula holds at that point. For instance, let's look at the case of diamond phi. Diamond phi holds at that point if there is a point which is accessible from that one for which phi holds. Now this interpretation that they sort of gave in words, it's there in the box, and gives you a translation of model logic into first-order logic with one free variable. And this is called a standard translation, so now that you have this map, let's say you can ask what's the image of it. And the answer is given by Van Benten's theorem, which says that the first-order formula with one free variable is the equivalent to the standard translation of the model formula if and only if it's invariant under a certain class of transformations between models that are called bisingulations. Bisingulation is a relation between triplet models that basically says that the two models have the same process structure, so to speak. If you know what a p-morphism, sometimes called also bounded morphism or open morphism, is, then a bisingulation is a span of such morphisms. This theorem usually uses some basic molecular tools, saturated elementary extensions. However, if you avoid the use of compactness, you again obtain a quantitative improvement, meaning that the first-order formula of quantifier record most k is preserved under by simulations if and only if it's equivalent to a model formula with a model depth at most 2 to the k. Model depth here is the maximum nesting of modalities. And the same proof with very little extra work gives you also a result for finite models. The third and last class of examples is that of homomorphism counting results. So such a result typically says something like two finite relational structures, let's say two graphs, satisfy the same properties in a certain given logic fragment, if and only if they cannot be distinguished by counting the number of homomorphisms into them from some sort of class of test structures. To state one such example, we can consider the category graphs and graph homomorphisms. And then, as a logic fragment, I'll take first the logic with added variables. That is, means all formulas that you can build starting from a fixed set of variables x1, xn. But you're also allowed to use so-called counting quantifiers. So for each positive integer I, that's a quantifier which says there exists at least I elements satisfying certain goals. And Vajra proved in 2010 that two finite graphs are equivalent in this logic fragment if and only if they cannot be distinguished by counting the number of morphisms into them from any finite graph, also called tree width less than 10. The tree width is a combinatorial parameter of structures that essentially tells you how far is the graph from being a tree or a forest. I should mention that the first homomorphism counting result was proved by Levas in 1967, and it was later generalized to certain locally finite categories by Alice Boult and Chanisbo, but I'll come back to this point towards the end of the talk. Okay, so now the idea is to develop, as I said, a categorical approach to resource-sensitive model theory, and the idea is to do so starting from the notion of game. So first of all, I should tell you, well, what are games, but also why games. And one way to motivate games is the following. So in model theory, and similarly in finite model theory, people are not interested in looking at objects up to isomorphism. They want to look at objects up to definable properties. So in classical model theory, that would mean, for instance, up to elementary equivalence. However, to finite models that are elementary equivalent, they are isomorphic, so that's not very interesting. That's why in finite model theory, they usually consider some small logic fragments, so some fragments of first order logic. And now, games are useful because they allow you to establish whether two structures are equivalent in a certain logic fragment, but more specifically, they are well suited for a fine analysis of logical resources. As we see, some notions of logical resources, such as the quantifier rank that I've mentioned, model depth, or the number of variables, they have a counterpart at the level of games. So, I'd like to recall one example of game, which is the best simulation game in modern logic. So, whenever I say game, I mean what is sometimes called a model comparison game. So, these are games that aim to establish whether two structures satisfy a certain sentence or not. And typically, you are interested in determining whether they satisfy the same sentences from a given logic fragment. So, these are two-player games. There is spoiler, there's duplicator, and this specific game is played on two-pointed triplet models, A and B, and it has an initial position, which is given by the two distinguished elements. At round I, if the current position is given by a pair of elements AI and BI, spoiler picks one of the two models, say model A, and an element which is accessible from AI. Okay, so you're moving along this accessibility relation. And duplicator has to respond with an element that is accessible from BI, so an element of the other model. If duplicator has no such response, then they simply lose. Otherwise, duplicator wins after k rounds if the pairs of elements, AI and BI, satisfy the same unary predicates, for each I between 0 and k. And this notion of game is motivated by this classical theorem by Ennis and Milner, which says that duplicator has a winning strategy in the k-round game if and only if the two triplet models satisfy the same model formulas with model depth at host k. Let me give you an example of this game. It's going to be a very trivial example, but it's 9 in the morning. So here you have two triplet models, and in red you have the two distinguished elements. So that's the initial position in the game. In the first round, the spoiler has to choose one of the two structures and an element in that structure. So let's say that it moves on the left-hand structure. And duplicator has to respond on the right. Okay, so let me step back. I should tell you something about my graphical notation. So the arrows, they denote the accessibility relation. That's pretty clear, I guess. And then you have circles and boxes, and you can think of them as being unary predicates. So what duplicator has to do at each move is to make sure that they can actually move along the accessibility relation, and if spoiler pick the circle, they should respond with circle, and similarly for box. Okay. So again, spoiler moves to the box, and so duplicator has to do the same thing, it couldn't do anything else anyway. And now spoiler in the second round moves but in the other structure, and duplicator moves in the first structure. Now spoiler moves in the first structure and duplicator responds in the second structure. This is after round 3 you can arrive at such a position, and so far so good in the sense that duplicator could respond in the correct way for the first 3 rounds. But this was duplicator's response to a very specific spoiler strategy, but in fact you can show that no matter how spoiler played in the first 3 rounds, duplicator couldn't respond correctly. This means that these two models satisfy the same model formulas up to model depth 3. However, as you can easily see, well, something is going wrong if you play around 4, because spoiler could play in the left structure, I mean, get to that circle, but duplicator could not respond in the other structure. It couldn't move anywhere. There are no more accessibility relations. So that's a formula model that 4 that distinguishes the two models, and it's a trivial one which says that there exists a path of that 4. But this trivial example shows a useful idea, which is that if you're only interested in the model theory of your Kripke model, you can equivalently look at a nicer model, which is called the tree unraveling of the Kripke model. So the idea is the following: you start from the two original models down there, the boxes with the distinguished elements, and you form another Kripke model whose elements are going to be the finite parts starting from the distinguished elements. Okay? And the accessibility relation is going to be the prefix order. Okay? So you have parts, and you can just say whether a path is a prefix of another, whether one extends the other or not. And you can also assign boxes and circles just by looking at the type of the last element along the path. As you can see, the tree unraveling of the first structure is infinite. That corresponds to the fact that you have a cycle in the model. The tree unraveling of the second structure is very much finite. And in fact, you can deduce the fact that a duplicator can win the first 3 rounds just by looking at these 2 trees, and you can count and find 3. In fact, everything you may want to say in the model language about those 2 Kripke models is encoded by those trees. So, as I said, this tree unraveling is again a Kripke model. Its distinguished element is given by the one element sequence. And it has a further property, which is pretty evident from the picture, which is that if you fix any element x in the tree unraveling, there exists a unique path starting from the one element sequence. Okay. Now, take a category of Kripke models at scale, and then take the full subcategory S of those Kripke models that satisfy that property star. What the tree unraveling is doing is to exhibit a right adjoint to the inclusion of S into K. So it's exhibiting S as a full co-reflective subcategory of K. Now the objects of S are usually called synchronization trees because they have this evident definable tree order. And now that's for the full unraveling, but you could, as I said, stop at bounded parts if you're only interested in properties up to a certain model depth. And that means that for each positive integer n, you can take the tree unraveling to depth n, and that gives you a co-reflection of k onto the full subcategory of synchronization trees of height n. Now, these co-reflective subcategories, you can equivalently view them as idempotent components on Kripke models. And in fact, this perspective, well, not really this comonadic perspective, but this use of unraveling model logic has long been recognized as a very useful tool. However, what was not recognized is that other notions of games can also be modeled in terms of components. And perhaps one of the reasons why this was not understood earlier is that in general these components are not idempotent. So this insight goes back to a paper by Samson Abramsky and Stadler and Wang in 2017. This started what we now call the program of data components. So in general, if you have such a component G and a structure A, you want to think of G of A as a sort of covering, as opposed to an unraveling of the structure A. By the way, here by covering, I mean in a very naive way. As we see in concrete cases, G of A is a structure whose universe is the set of all planes in A, so those are finite tuples of elements from A, and you have a map from G A to A, which is the co-unit of the component that simply outputs the last element of the sequence. but that's a subjective homomorphism. Now, before introducing a nice categorical answer framework to model these games, so you should have at least 2 examples. So the second example is going to be that of origin per se games, model view. And you can view these games by slightly modifying the by simulation game from other logic in the following way. Again, it's a game played by spoiler duplicator on 2 structures A and B, typically relational structures. There is no initial position in the game, and spoiler duplicator are not required to move along any accessibility relation. They can jump from one element to any other element. There's still the same constraint that if spoiler in a certain round picks an element in one structure, then duplicator has to respond with an element in the other structure. And duplicator wins after k rounds if the relation which is formed by the pairs of selected elements in these k rounds is a partial isomorphism between the structures. And the classical result by our for says that duplicator has a winning strategy in this k round game if and only if A and B satisfy the same sentences having a quantifier rank equals k.
Sorry, you said these comonads are not typically idempotent.
Yeah.
So how do you think about that comultiplication?
Right. If you can give me just 30 seconds, it's going to appear there. So, I'm going to extract a comonad from this game. So there's going to be one comonad, ek, for each positive integer k, and this k models the number of rounds in the game or the quantifier rank of formulas. So I'm considering a category of relational structures. So we're going to build one game comonad ek for each positive integer k. This is going to be a comonad on the category of relational structures. That's a category that is given by R. On objects, the comonad acts in the following way. So you have a structure A, and ek of A is going to be a structure whose universe is the set of all sequences of length at most k of elements from A. That's this unit here. So you can think of it as a set of plays of length at most k in the structure A. And now you leave the relations from A to k of A. Say, for instance, that you have a binary relation. Its interpretation in ek of A is going to consist of the pairs of sequences as T that satisfy 2 conditions. The first condition is that S and T are comparable in the prefix order, so either S is a prefix of T or the other way around. And the second condition is that if you look at the last 2 elements of the sequences S and T, they are related in the structure A. And this leads to a functor in the sort of obvious way. If you have a function from structure A to structure B, this leads to a function between 2 pairs of elements from A and B just by applying the function element-wise, coordinate-wise. The counit of the comonad, as I mentioned before, takes a sequence to its last element. So from a game theoretic perspective, that is telling you what was the last move played in that game. And the commultiplication sends a sequence to a sequence of sequences, namely this sequence of prefixes of that sequence. And from a game theoretic perspective, this is reconstructing the history of plays in the game. This gives a comonad on relational structures. Now, what is perhaps a bit surprising, at least this was surprising to me, is that while you have a comonad, you look at the coadjuvants for the comonad. And this turned out to capture precisely a combinatorial parameter of structures that is very useful in finite model theory, which is that of tree depth of the structure. I'm not going to define it, but it's very similar to the tree width parameter, at least in spirit. So I say that coadjuvants capture this parameter. What I mean by this? Well, I mean that a relational structure A has tree depth at most k exactly while it admits a coadjuvant structure for ek of A. So sorry, for the comonad ek. The reason why this theorem holds is in fact that you can give a a concrete description of the categories modulus for EK in the following way. The objects are relational structures equipped with the compatible forest order of height of most K. And these compatible forest orders are precisely witnesses for the fact that the structure has 3 depth at most A. And the morphisms are also easily described. They are the homomorphisms of structures that are also forest morphisms, so these forest orders. Okay, so you can capture these combinatorial parameters by looking at coalgebras for the comonad, but you can also capture preservation of logic fragments by looking at coalgebras. For instance, okay, we're working with the order of the second comonad, so we're working with I for k at the level of logic, so that's first order logic with quantifier ranking most k. If you work in the classically category comonad, then the homomorphismic reorder in the classically category captures precisely preservation of the existential positive fragment of F of k. And what is isomorphism in the classical category, that gives you precisely equivalence in F of k with counter quantifiers. What if you're interested in equivalence simply F of k? Well, it turns out that you can capture that, but you need to work in the category of coalgebras, the item of more coalgebras. The classical category is too small. In that case, it corresponds to having a span of open maps. So this is very much related to the notion of bisimilarity in modern logic that I mentioned before. I will not define open maps here because I will do that in a more abstract setting in a few minutes. And perhaps the main point here is that everything I've told you so far is not specific to bisimulation games, nor to only for say games. In fact, this has been extended to a number of other model comparison games. So there are game components for Pebble games, that capture finite variable logics. There are components for monadic second order logic, guarded quantifier logics, and so forth. And in each case, there are tight connections between coalgebras and combinatorial parameters. And in each case, you can capture preservation of logic fragments in categories of coalgebras. If you want to simplify and perhaps oversimplify, what's going on here is that we are starting from concrete notions of games. We are building from them resource index families of components and then considering categories of coalgebras for those components. So we are extracting categories from games. A natural question here is whether we could recognize which are the components arising in that way, and what are the categories that arise as categories of coalgebras for those components. Note here that there's no definition of game component. You know one when you see one, but so you might attempt to isolate some fundamental properties of these categories, and this leads to an axiomatic perspective that I'm going to talk about next. So in other words, what I want to do is to go the other way around. I want to extract games from categories. It turns out that you need pretty little structure in order to do so. So I'll be working with a lovely small and well-powered category, C, equipped with a proper factorization system. So this is an orthogonal factorization system, and the class of the left class of morphisms, the Q morphisms, I call them portions, and the right class of M morphisms, I call them embeddings. And the properness condition here says that every quotient is an epimorphism and every embedding is a monomorphism. If you have such a category, we can define what's a path. So a path is an object whose poset of M subobjects is a finite chain, finite linear order. And a path embedding is simply an embedding whose domain is a path. If you have any object X in your category, you can look at its poset of M subobjects, I call it poset of embeddings into X, and then there's a subposet which is formed by the path embeddings into X. And that's what I denote by PX here. And in fact, it's pretty easy to see that this poset is a tree, pretty much by definition of the path. And in fact, it's non-empty as soon as the factorization system is stable and your category has an initial object. So So let's assume that C has these properties. Then this amount of structure, what it allows you to do is to define outside games in your category. And if you want to play a game between two objects X and Y, essentially what you're going to do is to play a game of the associated trees. There are various notions of games that you could define, but they're basically all variations of one game, that is the one I'm going to define now. So again, this is played by spoiler and duplicator on two objects now in this category. And it's essentially the by simulation game that we serve from model logic played on the corresponding trees. So there's an initial position which is given by the roots of these, remember, non-additive trees. And the accessibility relation of the crypto model here would correspond to this immediate successor relation that you have in your tree. And at each round, what duplicators should do is to ensure that they're able to respond to the spoiler's move. And they also want to make sure that if spoiler picked an element in the first tree, which is going to be a path embedding into the object, say X, then duplicator should pick a path embedding into the other object Y in such a way that these two path embeddings have isomorphic domains. Now this gives you a notion of back and forth equivalence in the category C. But in general, which means concretely, what you want to do is not to study this notion of back and forth equivalence, but rather to transfer it to other categories, typically categories of structures, relational structures. This you can easily do by considering an adjunction between this category C and any other category E. And you transfer this back and forth equivalence simply by saying that two objects A and B in the base category E are back and forth equivalent if their images under the right adjoint are back and forth equivalent in the category C. In fact, all examples of game components that we have fit into this framework. Typically, E is the category of all relational structures, and C is going to be the category of coadjuvants for the component. And the abstract game that I've just presented, in fact, it coincides precisely with the concrete notion of game built by simulation or part of the same game. Now you may wonder how much did we generalize? So this R back and forth equivalence, does it have anything to do with logic in general? It turns out that in the case where you are working essentially locally phonetic presentable categories, then the answer is yes, it has to do with logic. So if you assume that C and E are locally phonetic presentable categories and R is a morphism of locally phonetic presentable categories, then under mild assumptions, you can prove that this R back and forth equivalence is always contained in equivalence in L infinity omega. And that would be first the logic with arbitrary set index conjunctures and disjunctures.
What do you mean by morphism of locally presentable categories?
Here I mean that R preserves filtered limits. The proof, as you may guess, uses Gabel-Ullmann duality. But as a subtlety here, and I'll explain it very briefly, so the main technical point is to establish that path embeddings in C are definable in your logic, in a sense. And you do that by first moving to the category E and then going back. So if you want to move to the category E, so to speak, you're going to use the dual of R under Gabel-Ullmann duality, and that gives you the translation at the level of logics. But you don't have a morphism of locally phonetic presentable categories in the other direction. So that's where the troubles start. And for that we use a construction that Orgis introduced, and he called this construction the word construction, that essentially gives you generalized translations as soon as you have a factor that preserves filtered limit. Now, if you start with a game component and look at the category coadjuvants, this will have a nice factorization system, just like the ones I was considering. But so you can define paths, path embeddings, and so forth. But what happens is that these categories coadjuvants typically have much more properties. And crucially, one property that holds in each case is that a full subcategory of parts is dense. And these extra properties lead to what's called an arboric category. Now, I don't want to give you the details of the definition. It's not complicated, but it will take a little bit of time. So I'll just tell you what's perhaps the most important property of these categories. Namely, that this notion of back and forth equivalence, defined in terms of gains in the category, happens to coincide with bisimilarity in the sense of Julia, Wilson, and Ginsko. And I recall now what that means. So say that a morphism in a arboric category is open if it has the right lifting property with respect to all morphisms between parts. Then bisimulation is a span of open morphisms. Okay? So two objects are bisimilar if such as expand, connect, and them exist. So that's the notion of openness that I was mentioning over and over again in the book. So from this perspective, equivalences with respect to number of resource index logic fragments can be captured in examples simply by transferring this bisimilarity relation defined in terms of spans of open maps to other categories along an adjunction that is called here an arboric adjunction, but it simply means that the category C has this arboric structure, but the adjunction could be any adjunction. In particular, this gives you a slightly different perspective on preservation of logic fragments. So, for instance, preservation of existential fragments typically amounts to building a cocoon of embeddings in your category. And if you are interested in preserving existential positive fragments, that's the same thing as building a cocoon of morphisms. Now, I guess I have a few more minutes. So I'd like to revisit some of the theorems that I presented at the beginning from this categorical perspective and see what we get there. So I mentioned that the prototypical homomorphism counting result goes back to Levas, 1967, for finite relational structures, and it says that two such structures A and B are isomorphic if and only if they cannot be distinguished by counting the number of morphisms from any other finite relational structure. So you can view this as a sort of unnatural unit dilemma. And this was later generalized to locally finite categories with certain factorization system by Aleshford and John Isbell, as I mentioned before. And if you combine this categorical perspective, which uses locally finite categories with gain components, what you get is essentially a uniform approach to homomorphism counting results defined in model theory. So these results were typically improved using different techniques. But for instance, you can prove a general result, and for the identity component, what you get is the last result. If you apply it to the Orenfeld-Fassé component, you get a result that was proved by Martin Grohe in 2020, which says that two finite structures are equivalent in first-order logic with quantifier rank k and counting quantifiers, if and only if they cannot be distinguished by counting the number of morphisms from finite structures having tree depth at most k. Similarly, you can also obtain new homomorphism counting results for grading model logic, okay, by using the model components given by those highly important adjunctions that I discussed earlier. So, if you look at that theorem, item 1 is saying precisely that the co-free coadjuvants on A and B are isomorphic in the classic category. That's something I mentioned. Isomorphism in classic category captures equivalence in those logic fragments with counting quantifiers. And item 2 is saying that those co-free coadjuvants cannot be distinguished by looking at the number of morphisms from finite coadjuvants. So in that case, you can simply consider the category of finite coadjuvants for the component Ek, and then an abstract categorical version of Levas result will be this theorem here. Interestingly, you can not always assume that co-free coadjuvants are finite. Right? So in fact, in Van Jacques' result that I presented at the beginning, for tree width instead of tree depth. They could free coalgebra on the finest structure infinite. So it turns out that in that case, you can still recover the result using a more more general approach, which essentially relies on the fact that although these free coalgebras are infinite, their endomorphism monoids are finite. And you combine these observations with some tools which are tightly related to some work by Marcelo Fiore and Matthias Menni on algebras for factorization monoids, in the sense that some of their results generalize some of the tools that we use in homomorphism counting. I also mentioned homomorphism preservation theorems at the beginning. In fact, you can phrase and prove some of these results in these orthogonal categories, using these orthogonal junctions. And some of them admit 5-line proof. Really easy, and that's the case, for instance, for modern logic and Gaudian logics. And they also need relativizations to certain subclasses of structures, for instance, finite structures, and that's the case as soon as you come on and illustrate, so that's a subclass, basically, you get a relativization. But those examples are very well behaved, and that's not the case in general. It turns out that we can get a fully axiomatic proof of Rosman's theorem HPT, the other categories, but that's very far from being trivial. But the idea is easily explained, and in fact it goes back to the paper by Rosman himself. The idea is you find it all the time in finite model theory instead of upgrading. So you have two objects A and B that are in some sort of weak relation between them, and you want to build extensions A star and B star that are in a certain final relation. Concretely here, what it means is that if you take A and B and look at their images under the right adjoint, they are going to be homomorphically equivalent. And you want to find A star and B star whose images under the right adjoint are back and forth equivalent, or completely bisimilar. And the way you do this is essentially via a sort of small object argument. And this can be carried out in orthogonal categories under appropriate assumptions. I'll conclude by not mentioning what I haven't mentioned. People have done a lot of work in several directions, and I haven't mentioned all these directions, but I'd rather mention some directions for future work. One of them would be finding new examples of orthogonal categories, and that would naturally lead to applications of this axiomatic framework of orthogonal categories and orthogonal junctions outside of model theory and finite model theory. Another one has to do with translations between logic fragments. That's something that you're usually interested in logic, how do you translate from one logic into another, and that translates into morphisms between orthogonal categories. So a natural thing to do from this viewpoint would be to look at a category of orthogonal categories, and this hasn't yet been done, at least in a systematic way. And a third and last item, which is the one I'm very interested in at the moment, is to possibly develop a sort of homotopy theory of logical resources. And what I mean by this is that the motivation really comes from some technical considerations, especially with regards to these upgrading arguments that are pervasive in finite model theory. I think it would make a lot of sense to see these as instances of fibrant replacements with respect to some appropriate model category structure. And you would look at such a structure naturally on the category of presheaves over the category of paths category. And thank you very much.
Very much. Questions over there?
Thanks very much for the talk. This is a general question about finite model theory. important results about finite models whose only known proofs use compactness?
I would say no, in a sense. I was trying to think which proofs finite model theory use compactness. People, but that's also a choice that people usually choose to avoid using compactness. So if they can use anything which is not compactness, they do that. They can use games or harmonics instead. No, I can't think of anything.
Well, I know it sounds kind of implausible, but you know how there are results about the real numbers or even the naturals that use large cardinals, these odd requirements. Okay, thank you.
Thank you. Thank you very much.
Thank you very much for a nice talk. I do love a categorical approach to something. I may have missed the answer to this, you may have already answered it, but I was thinking about something else you said. So when you had the categorical, you said that all concrete game units fit into that categorical framework. Did the framework provide you with some new examples that you would not otherwise have thought of?
You mean examples of games? That's a good question. So the quick and honest answer is no, but I think in the sense that what people have been doing was to start with some concrete notion of game, because that was interesting in finite model theory and had application of that, and try to understand that from a commonality perspective. But of course you might try to go the other way around. I think that's related to what I was mentioning about having new examples. So for instance, we haven't really found any application of this yet, but you can prove that if you have a forest border and you take push shifts over that, that's a model category. So you have a notion of game. Is that interesting? I don't know, we haven't found any applications yet, but yeah, that's really helpful. Thank you.
Other questions?
You mentioned the work of Macchiarini and Marcello Fiore on factorization models. Is your approach with Abramsky, which associates to a factorization system in class objects, is this somehow the idea? Because if you do something with the factorization system as a category theorist, I would like to understand what you're really doing. So is there some category theory behind these arboreal categories associated with the factorization system?
Okay, so what I can do, well, just already said that, but just to make it clear, so the notion of path, the notion of path embedding, virtually any notion that you're considering of other categories, they are all induced by the choice of the factorization system. So the factorization system determines everything else. The path depends on the notion of factorization system. Now, if you could somehow, I don't know, that's a good question. Okay, I'll think about that, but perhaps I should mention something just to clarify, because I was briefly mentioning the work of Marcelo Matthias with regards to homomorphism counting results. So the connection between their work and ours is more at the level of these results. So it doesn't really have much to do with the categorical setting. It has more to do with homomorphism counting. And homomorphism counting intersects with these other categories simply because you, in the applications, you want to apply this abstract homomorphism counting result to categories of quadrats for game models. But the fact that they live in an umbrella setting, that doesn't play any role whatsoever. So that's why I don't really know what to say about the interaction of the two. I'll think about that. Thank you.
Matthias.
Your last slide mentions three-shift categories.
Yes.
It's very tempting to try to give a definition of a path object in the total process. So the first naive suggestion is to consider the objects such that only to the field is totally ordered. That's probably too naive, but if it has any like free things from being in a appreciate value, it might lead to something in an elementary problem. It's just a problem.
Perhaps I should mention that like the parts there, but also if you take like you take like a forest and take precision over that, then the parts are just the representative ones and the initial object. Much more, but it's just for precision over forces in general. You might have something which is
Yes, it should be an elementary.
There is another question. Mark?
Yes, so if you consider first order logic, right, then there is a notion of an ultra-category, which is axiomatizing, models of first order theory with the help of ultra product and some connection between them. What do you think about a similar notion here, that you have something that axiomatizes finite models of a theory, and instead of using ultra products, you are using these commonas as a structure, so that preservation of the structure is kind of should somehow correspond to interpretation between logic theories. Right?
That's a good point. I haven't thought about that too. Okay, perhaps I should just mention that Mackay's approach was not an approach to categorical model theory that I should have mentioned at the beginning. Yes, that's a good idea. Because in a slightly different direction, so what you want to do with that, the reason why you consider ultra categories is because you want to be able to recover theory from your category models, right?
Well, that can do many other things. I mean, strong duality is not just recover Boolean answers, right? I mean, we are using it, right? And the same thing is happening in ultra categories.
So what the component is doing here is to, so I haven't mentioned this, but so these are all graded components. So the main purpose of these components is to capture this fact that you have a typically increasing amount of resources that you may want to consider. So it's like considering a sort of stratification of your logic into small fragments, which may be not finite. So there might be connection, but if you, I don't know, if I think of ultra categories in you're not stratifying in terms of some syntactic notion.
I don't think about such a simple analogy. Probably you have to have a shift, right, between components and your notion of a model, right? But just to use a bunch of components as a structure of the finite, the category of finite models so that it tells you something about the theory, right?
Could be. That's very interesting idea. Thank you.
Any more questions?
So, I have also these theorems that the surjective monomorphism preserves positive sentences. So it's kind of. I'm wondering, do you know of theorems that try to generalize these things out of the category of sets? So usually the first order models will be set-based models, and these properties are preserved in that context. But what I'm interested in would be lifting these theorems to more categorical settings. Do you know work on this side?
Can't think of anything, but I would have to think a bit more about that. Yeah, I don't know. Thanks.
Let's thank